Hi everyone. Thanks for coming to my talk and thanks so much for inviting me. Yeah, as said, I'm going to be talking about generalized convex toric domains and symplectic embeddings. This is all joint work with Dan Cristofaro-Gardiner and Dusa McDuff. So to begin, I'm just going to define some basic things that probably you all already know the definitions of, but we'll just get it out of the way. So a symplectic manifold X is a manifold X with a non-degenerate closed two-form omega, the symplectic structure on our manifold X. And Darboux theorem states that locally all symplectic manifolds of the same dimension look the same. So we can find coordinates x1 up to xn and y1 up to yn on X such that omega looks like this standard symplectic two form here, which is just the sum of dxi wedge dyi. And for the purposes of this talk, we're just going to be thinking about four-dimensional symplectic manifolds. And our manifolds are all just going to be embedded in R4. So we're just going to have this standard symplectic form on R4 restricted to our manifolds, but we'll get to that in a second. So we're going to be thinking specifically about symplectic embeddings of our symplectic manifolds. So a symplectic embedding from one symplectic manifold to another is a smooth embedding where we want to preserve this symplectic structure. So we want the two form on the target to pull back to the two form on the domain. And one consequence of having a symplectic embedding is, well, when you have a non-degenerate two form, it's going to induce a volume form on your symplectic manifold. And so if you preserve this symplectic structure, you're going to preserve your volume form. And so if you have a symplectic embedding between two symplectic manifolds, then the volume of the domain has to be less than or equal to the volume of the target. So in this talk, we're going to be thinking about obstructions to symplectic embeddings, and this is our first example of an obstruction to a symplectic building, a symplectic embedding, in the sense that if the volume of x1 is too large, then we know we cannot have such a symplectic embedding, and this is the trivial obstruction in the sense that we always have this obstruction, and the other obstructions will think about what we'll see that they don't always obstruct symplectic embeddings from happening. So while I've mentioned that there are other obstructions, but how do we know that? Maybe symplectic embeddings are the same as just volume preserving embeddings. Well, Gromov showed that in his famous non-squeezing theorem. And what his theorem states is that if there is a symplectic embedding between a 2n dimensional ball and a cylinder, this embedding preserves the symplectic structure if and only if the radius of the ball is less than or equal to the radius of the cylinder. So you cannot squeeze a bigger ball into a skinny cylinder and preserve the symplectic form. So obviously the ball has finite volume and the cylinder has infinite volume. So there are some non-trivial obstructions other than the volume obstruction that are obstructing this embedding. Okay, so we're going to be thinking about embedding generalized convex toric domains. So I put generalized in parentheses here because for the rest of the talk, I will just refer to these as convex toric domains. But in the literature, often convex toric domains refers to something more specific than what I'm going to currently define. So A generalized convex toric domain, X omega in C2 or R4, is the preimage of a compact convex region omega in the positive quadrant of R2 under the moment map here. So Z1, Z2 maps to pi norm Z1 squared, comma pi norm Z2 squared. So if this is an example here where my compact convex region omega is this triangle here. And if I look at the preimage under this map, I'm going to get a four-dimensional ellipsoid where A and B are going to determine the eccentricity of my ellipsoid. And I'm going to refer to this ellipsoid as EAB. And you can take other regions. So here's just some three examples of omegas that I can choose. So if you haven't thought about this before, something to note is that points on the axes are different than points in the interior. So for let's think about the ellipsoid. If we look at the boundary of the triangle, we have, the whole purple line I've drawn here, but the points on the axes are going to be in the interior of my convex toric domain. So just the hypotenuse is going to be the boundary of my ellipsoid, while for some shape like this circle here, that's off the axes, the whole boundary of my omega is going to be the boundary of my convex toric domain. Something else to note if you haven't thought about this before is that the preimage of a point on the interior of the quadrant is going to be a torus. The preimage of a point on the axes is going to be a circle, and the preimage of the origin is going to be a point. So all of these convex toric domains are symplectic manifolds where we're just going to take that standard symplectic form on C2 or R4 and restrict it to our convex toric domain. And we're going to scale the volume. So the volume of the convex toric domain is equal to 2 times the area of omega. So if the nice thing about that is if your ellipsoid is actually a ball, so A equals B, then your ball of size A, your triangle of size A, just has area A. I mean volume A. Okay. So what we're going to do in this talk is we're going to consider how the boundary of omega impacts symplectic embedding problems. And the two things that we're going to focus on, which I'll define or be more specific about later, are the affine perimeter of omega and the curviness of the boundary of omega. So the first thing before I state one of our main results is I need to define for you what this this affine perimeter is. So well, one reason why we have this affine perimeter rather than, I mean, you could take the normal Euclidean perimeter, but these convex toric domains are invariant under SL2Z transformations. And so we would like to have some perimeter quantity that's also invariant under these SL2Z transformations. And because the SL2Z transformation is like some torus action on your convex toric domain. And so, okay, what is the affine perimeter? Okay, so if we just have a line segment, let's say that it goes from 0, 0, the origin, to some point CD, and this line segment has rational slope. So here I'm saying the slope is B over A, where this is written in reduced form. So the GCD of B and A is 1. Then the affine length is just going to be the number k that we multiply by AB to get to the NCD. So in this example here, my primitive direction is I move 2 over and then 1 up. And you can see that in this line segment, I moved 2 over and 1 up once, twice, and a half of a time. So the affine length of this line segment here is 2 and a half. Another way to say this is that the affine length of a line segment S of rational slope is the Euclidean length of its image under any SL2Z transformation A, such that the image of the line is contained in the x-axis. So here I would be taking, well, I could take some SL2Z transformation that maps 2, 1 to 1, 1, 0, and then the length is just the Euclidean length on the x-axis. So if your line is on the x-axis already, then the affine length is just the Euclidean length. So the affine length of a line with irrational slope is 0. There's no transformation such that you can send it to the x-axis. And additionally, if you have some non-linear segment, so some curvy segment, the affine length of that line segment is also going to be 0. Okay, so then the affine perimeter is just the sum of the affine lengths of the various sides. So for this example here, this side has affine length 2. This guy also has affine length 2. I'm moving in the 2, 1 direction again. And this has affine length 0. It's a non-linear component. And so the perimeter is 4. If I have a ellipsoid, it depends on if this A here is rational or not. If A is irrational, then the slope of this hypotenuse will be irrational, and so it has 0 affine length. So the perimeter is just going to be 1 plus A. But if A is rational, then the hypotenuse has contributes to the perimeter, and you get some other quantity here. So in some of the results I'll state later, we'll be assuming that we have some irrational ellipsoid, and like one of the reasons that's very important is that this perimeter quantity is just 1 plus A, and we don't have this extra little 1 over Q factor here. Okay, so I have to tell you about one more thing before I can state one of our results. So the next thing that I will tell you about is ECH capacities. These were defined by Hutchings. So for right now, I'm just going to give you tell you some properties these ECH capacities satisfy, and not tell you about anything necessary to define them. So for convex toric domains, there exists a sequence of non-negative numbers. These are all finite, called ECH capacities, and they have the following properties. So for us, one of the well, all of these properties will be important, but why we care about these ECH capacities for symplectic embeddings is they satisfy this monotonicity condition. So if ECH capacities are defined for X and X symplectically embeds into X omega, then for each K, we get that the ECH capacity, the kth ECH capacity of X is less than or equal to the kth ECH capacity of X omega. So these ECH capacities can possibly give us more obstructions to symplectic embedding. So just like the volume obstruction that we started talking about. If the K, if for just one K value, the ECH capacity of X is bigger than that of X omega, then we know that we can't have a symplectic embedding. And these capacities end up being very useful in this setting, in the sense that they do often give you obstructions, and they often tell you when something cannot embed in another, in something else. Okay, they also satisfy this scaling property here. So here, when I mean R times X omega, I mean that I'm scaling my symplectic form by size R. In the picture of my of omega, you can just also scale your region in R2 by size R. Okay, and then they also satisfy this volume principle, or what is known as the Weyl law. Why it's called this is this is fairly reminiscent of Weyl's original law, and his original law was about the asymptotics of eigenvalues to the Laplacian operator that satisfied Dirichlet boundary conditions. But what he showed is that the asymptotics for the eigenvalues of that operator recover the volume of your domain. And so this is a analogous kind of statement, so that the leading asymptotics of our ECH capacities recover the volume of our convex toric domain. This property is well, it shows that these ECH capacities are like detecting something important about like the symplectic invariance. The volume is in a basic symplectic invariant, and the ECH capacities can detect this volume quantity. Okay, and then finally, we have this disjoint union property. So you don't really need to pay attention to exactly what this inequality is. The point is just that if you have a disjoint union of convex toric domains, symplectically embedding into some other domain X, then you get this inequality on the ECH capacities of the convex toric domains. But again, this specific inequality doesn't matter, but later I will mention that like we used this property for something. Okay, so now I can well, I can almost say the result. Okay, so as we just saw on the last slide, this property here is about the leading asymptotics of our ECH capacities, and we're going to consider the subleading asymptotics of our ECH capacity. So we're going to take the CK, and we're going to subtract the leading term. So that's what I've done on this slide. If you remove the limit and solve for CK, you'll get this root 2K times the volume. And so we're going to take our ECH capacities and subtract the leading term, and define these subleading terms EK of X. Okay, so here's an example. So the ball, which is just the convex toric domain corresponding to this triangle of size 1. So the volume of the ball is just 1, and the perimeter of the ball is 3. Each of these guys have affine length of 1. Okay, so the ECH capacities of a ball are, well, I'm not going to justify this for you, but we can write them as the kth ECH capacity of the ball is n if k is in between these two numbers here. So if we're trying to find the subleading asymptotics, so the volume is just 1, so EK is going to be ck minus root 2k. And so EK is going to be most negative when we're subtracting the larger k value here. So when we're subtracting k is n squared plus 3n over 2. And it's going to be most positive when we're subtracting the smaller k value. So that'll be n squared plus, these both say n squared plus 3n over 2. But that should be n squared plus n over 2. So if you take the lim inf and the lim sup of your EK terms, you're going to get the lim inf is negative 3/2 and the lim sup is negative 1/2. So something to note here is that this 3 is what we just said was the perimeter of the ball. So this thing here is equal to negative perimeter over 2. So previously, Hutchings considered these the subleading asymptotics of the ECH capacities for convex toric domains, and he specifically restricted two cases where omega contains a neighborhood of the origin. So you have some interval on the y-axis, some interval on the x-axis, and a strictly concave curve from 0a to 0b. And in these cases, he showed that the limit of the EK terms is equal to negative perimeter over 2. So in these cases, when this is a strictly concave curve, it will always have no perimeter. So the perimeter will just be a plus b. So he showed in these cases, the limit is negative a plus b over 2. Okay, so we generalized we kind of generalized what he did here to our generalized convex toric domain case, and we showed that for our generalized convex toric domains, the lim inf of the EK terms equals negative perimeter over 2. So as you saw in the ball example, that for all convex toric domains, it's not the case that the lim inf is equal to the lim sup, like in the case Hutchings considered, but we do get this result on the lim inf. Okay, so the plan for the rest of the talk is I'm going to tell you a bit about the proof of this theorem, and then we're going to apply this theorem to our settings of symplectic embedding. So we're going to consider cases where for our symplectic embeddings where we have full fillings, because then the volume of our domain and our target will be the same, and then we'll see that these subleading asymptotics give obstructions to specific symplectic embeddings. But before we get into the applications of this theorem, we'll talk a bit about the proof of the theorem. Okay, so one important lemma to prove the theorem is that so this lemma is also a generalization of work of Cristofaro-Gardiner, where, so I guess maybe I should have said this earlier, but often for convex toric domains, people assume that your convex toric domain is on the axes. It contains a neighborhood of the origin, and some of what we did is generalizing the results to that case where you move away from the origin. But I guess also in the previous case, this weight sequence here was finite. But okay, that's okay. So the lemma says that for convex toric domains, there's a sequence of positive numbers, b semicolon b1. This could be infinite, such that the kth ECH capacity of your convex toric domain is equal to the minimum over this sum of ECH capacities, where these guys are all balls. So to find the kth ECH capacity of x omega, we need to understand the ECH capacities of balls of size bi. Okay, so why do we expect this lemma to be true? Okay, so we start off with some our region omega, and then what we're going to do is we're going to move omega so it touches the axes. So this process I'm about to describe is very analogous to the case where omega is on the axes. But the difference is that we're going to look for the smallest triangle, the smallest isosceles triangle that contains omega that's tangent to the boundary of omega. So here that's this triangle of size B. And then we're going to have generally three regions that are the complement of omega inside our triangle. So here we have omega 0, omega 1, and omega 2. Okay, so each of these regions, so this picture is specifically about omega 1. So this corner up here of omega 1, these two vectors form an SL2Z basis. So there's or a Z2 basis. So there's a SL2Z transformation that maps this this region omega that maps this point to the origin. And and this will be some concave toric domain at the origin, like this shape that I've drawn here, which I'm now calling omega 1 upper index 0. Okay, so now when we have this concave region, we're going to look at the largest triangle that, again, we were thinking of this triangle as a ball. So again, we want some isosceles triangle here that is contained inside our concave region that's tangent to the boundary. So here, that's this triangle I've drawn here of size B1. And then what I'm going to do is I'm going to look at the complement of that triangle inside of my concave region. And I have these two new concave regions that are the complement, this guy here and this guy here. Okay, and I can do the same thing for omega 2. I've split it up here, and the same thing for omega 0 down here. And now I'm going to keep iterating this process where now at each step I'll get two new concave regions, and I will keep doing this process. And so this is how I get my weight sequence of the first number before the semicolon is this big B, and then I have all my BI's coming from dividing up these concave regions here, omega 1, omega 2, and omega 0. Okay, so by definition of the weight sequence that I just defined for you for omega, there is a symplectic embedding of the convex toric domain x omega and the disjoint union of these BI balls into the ball of size B. So in this picture, what I've done is I've split up this ball of size B into omega and a bunch of triangles, which are SL2Z equivalent to my standard triangle. So I have this symplectic embedding here. And so because of monotonicity of ECH capacities, I get this inequality on the ECH capacities. So so what I'm trying to prove right now is that the kth ECH capacities of x omega is equal to this guy here. So this gives me one direction of my equality. So the other direction of the inequality that I'm not going to go into the details about, but it uses another way to compute these ECH capacities, which relates to counting to lattice points. Yes, but I'm not going to talk about that direction. Okay, so that was the lemma. It gave us a way to compute the kth ECH capacities of x omega related to the ECH capacities of balls. Okay, so again, remember that we're trying to prove that the subleading, the lim inf of the subleading asymptotics is equal to negative perimeter over 2. So something to note is that for a convex toric domain with this weight sequence here, then the perimeter of your convex toric domain is equal to 3b minus the sum of the bi's. So again, this sequence can be infinite. It will be infinite whenever you have a nonlinear segment or when your linear segment has irrational slope. But the sum of the bi always converges. And the volume is equal to this expression here. So we can also write the perimeter and volume in terms of our weight sequence. Okay, so again, this is what we're trying to prove, that the lim inf of the EK is equal to negative perimeter over 2. Okay, so I'm not going to say that much more about the proof, but basically we use this lemma that I have slightly justified for you guys. So we show that these are equal by using the ECH capacities for balls. So as I wrote on a previous slide, when we looked at the ball example, we can write what the ECH capacities for the balls are. So we use the ECH capacities for the balls to estimate what these EKX omega terms are, because again, these are just the ECH capacities minus the volume term. And the argument is partially some kind of optimization argument where we're looking for various k values where we expect like some sequence of k values where we suspect that these subleading asymptotics are going to be small, and then for those particular that particular sequence of k, then we estimate what the EK terms are. And the perimeter term comes up as this 3b minus sum of bi. So yes, okay, so that's my somewhat justification of this theorem. But now we're going to see some applications of the theorem. Okay, so the first application is going to relate to symplectic packing. So in symplectic packing, often the motivating question is what is the maximum volume of a symplectic manifold that can be filled with d disjoint balls of equal size? So some early result about this is for every d larger than 9, you can fully fill the volume of the ball of size 1 with d balls of equal size. Okay, so for us, we're going to be thinking about so often when people are thinking about symplectic packing, they're thinking about filling a symplectic manifold with balls. And here we're going to think about what happens when you try to pack a symplectic manifold with something else. So let's define something. So we're going to say that a symplectic manifold x1 fully fills x2 if when you scale that there always exists a symplectic embedding of the scaling of x1 into x2 whenever the volume of your scaled version of x1 is less than the volume of x2. And we're going to say that packing stability holds for x1 into x2 if for sufficiently large D, the disjoint union of D copies of X1 fully fills X2. So we want some finite value of D where we can put D copies of X1 into X2. Okay, so as I said, in the literature, packing stability often assumes that X1 is a ball, and much is known about this case. So Meyer just put up a new result, often talking about cases where packing stability holds in much generality. And Cristofaro-Gardiner and Hind, they gave some examples where packing stability does not hold. But we're going to be thinking about cases where X1 is not a ball. Okay, so the first application of our subleading asymptotics result is that a finite number of zero perimeter domains can never fully fill a ball. So packing stability does not hold in this case where your domain is a zero perimeter domain and you're trying to embed it into a ball. So this is a picture of a zero perimeter domain. But you could also have some polygon that's off the axes where each side of the polygon has irrational slope. So it doesn't necessarily need to be some curvy thing like this, but it just has to have zero affine perimeter. Okay, so the proof of this theorem is fairly immediate from our result, but let's go through it. First, we're going to let x1 and x2 denote convex toric domains with the same volume. And we're going to assume that x1 fully fills x2. And then we get this inequality on the affine perimeter. So the perimeter of x1 has to be bigger than or equal to the perimeter of x2. So something to note about this inequality is that it's maybe the opposite direction that you might expect, like it's the opposite direction of the volume condition. We're embedding x1 into x2, and we need the perimeter of x1 to be bigger than the perimeter of x2. So this condition about the same volume is very important for us because, again, we're going to use this result on the subleading asymptotics. And so for that to be an obstruction, we need the leading asymptotics to be the same. So we need to have this condition about the same volume. Okay, so the proof of this lemma is that the monotonicity and scaling properties of ECH capacities, because we have this fulfilling, we have this embedding of lambda times x1 into x2. And so we get this inequality on the ECH capacities of x1 and x2. Okay, and so as I was just saying, as x1 and x2 have the same volume, this implies that we also get this inequality on the EK terms, because these are just CK minus the root 2K volume term. And because both of these subleading asymptotics are just the negative of the perimeter over 2, then we get that the perimeter of x1 is bigger than or equal to the perimeter of x2. So it's because these guys are the negative of the perimeter that we get the opposite direction on the inequality for the perimeter. Okay, so the result I just told you was for our convex toric domains, and we're trying to say something about packing a disjoint union of these convex toric domains. So something to note is that the lim inf of the EK terms of a disjoint union of convex toric domains is not equal to the negative perimeter of the disjoint union of the convex toric domains over 2. So for example, for a ball, if you take the disjoint union of two balls, the lim inf of the EK terms is -2, while the perimeter is just the perimeter 3 plus the perimeter of the other 3, which is 6. But we do have that if X is the disjoint union of these R convex toric domains here, then we do get this this inequality of the lim inf of the EK term. So and the proof of this lemma just uses the disjoint union property I mentioned and the Weyl law of ECH capacities. Okay, so from these two lemmas I've stated, then we basically, well, we immediately get this lemma here. So if we have n convex toric domains and we let X be a convex toric domain and we assume there exists a fulfilling of the disjoint union of the n convex toric domains into X, then we get this inequality on the perimeter. So the sum of the perimeter of the x omega i's has to be bigger than or equal to the perimeter of X. So then we can immediately apply this lemma to our packing case where if we take x omega to be a convex toric domain with 0 perimeter, then our rescaled copies of x omega can never fully fill a ball because the perimeter of a ball is 3 and the perimeter of these guys just by assumption is 0. Okay. I should say that we also showed that that this corollary is also true for embedding the disjoint union of these convex toric domains into CP2 and not just a ball. So that these are rescaled copies of x omega can also never fully fill CP2. Okay, so that's one example of a application, and another example of a application is going to relate to the ellipsoid embedding function for x omega. So for each omega, you're going to have this this function C sub omega z, and the function is going to be the infimum of lambda such that the ellipsoid E1z symplectically embeds into lambda times x omega. So here is a picture of the function when omega is the ball. And this function was computed by McDuff and Schlenk. And the blue function here is the picture of the function, and the red curve is the lower bound coming from the volume obstruction. And what McDuff and Schlenk showed is that before this black line here, the function is piecewise linear. And it has these non-smooth points, these corners you can see. And they showed that there's infinitely many of these non-smooth points that accumulate to this value here. And when the ellipsoid embedding function for a convex toric domain has this property that we have these infinitely many non-smooth points accumulating to some finite value, we say that the ellipsoid embedding function has an infinite staircase. So one question which is somewhat difficult to answer is for which omega does the ellipsoid embedding function have an infinite staircase? So as I just said, the first work about this was McDuff and Schlenk showed that the ball has an infinite staircase. Cristofaro-Gardiner showed that the only rational ellipsoids with infinite staircases are scalings of E12, E1 3/2, and the ball E1 1. And certain families of polygonal convex toric domains with rational slopes have been studied extensively, but in general, it's difficult to say when some convex toric domain has an infinite staircase. Okay, so something else that we generalized in our paper related to these infinite staircases, which will relate to our application of the subleading asymptotics, is this accumulation point theorem. So what this theorem says is that if your ellipsoid embedding function has an infinite staircase, then it must accumulate at the larger solution A0 to this quadratic equation here. And also at that accumulation point, your ellipsoid embedding function must equal the volume obstruction. So if you gave me some domain omega, then I would find the perimeter of it in the volume, and then I would find the solution to this quadratic equation. And the larger solution, A0, that's where this black line is. And if there will be infinitely many non-smooth points, then they must accumulate at that black line. And the second part tells me that at that black line, the blue function must equal the volume obstruction. So it's saying that the black line, the solution to this equation, the volume obstruction, and the blue function must all intersect if there is a infinite staircase. So Cristofaro-Gardiner, Holm, Mandini, and Pires first showed this result for convex toric domains that are polygons that contain a neighborhood of the origin, and the polygons all have rational slopes. So that rational slope condition means that weight sequence, the B and the BIs, is a finite sequence. And so we generalize it to our more general setting. Okay, so that was a lot of information to tell you this this application of the subleading asymptotics. Okay, so if X is a convex toric domain and A0 is this accumulation point, so it's that solution to that quadratic equation, and we let A be less than the accumulation point and assume that A is irrational, then the ellipsoid E1A cannot fully fill X. So to visualize this corollary for the function, so if I plot the function, again, the function is the blue curve, and my volume obstruction is the red curve. And A0 here, the black line, is my accumulation point. Then if before the black line, the function touches the red curve, I know that that value of A has to be rational. So you cannot, so a fulfilling here corresponds to the blue curve intersecting the red curve. So before the accumulation point, you cannot have irrational ellipsoids that fully fill convex toric domains. So this corollary is sharp in the sense that there are examples where you have rational ellipsoids that fully fill convex toric domains when A is less than the accumulation point. So for instance, again, this is the picture of the ball, and you can see that before the accumulation point at A equals 4, you have this fulfilling, and also that there are irrational ellipsoids that fully fill X omega at the accumulation point. So in this for the example of the ball, the accumulation point is at some irrational number, and you get a fulfilling there. So we have that these irrational ellipsoids can't fully fill before the accumulation point, but there are examples where they do at the accumulation point. And the proof of this theorem is also fairly, well, is quite straightforward from the subleading asymptotic. So the perimeter of the irrational ellipsoid is just 1 plus A, again, because the hypotenuse isn't contributing anything to the perimeter of the ellipsoid. And so as a fulfilling exists, we have that the volume of the ellipsoid equals A, and so that must also equal the volume of X. And then the subleading asymptotics tell us that we get this inequality here on the perimeters, that the perimeter of the domain, the ellipsoid, has to be bigger than or equal to the perimeter of our convex toric domain. And if you rewrite this some other way, adding the volume term, you get this inequality here. And then if you simplify this, you get exactly the accumulation point theorem for A. So remember, the accumulation point A0 satisfies this quadratic equation, this equals 0. And so we conclude that the size of our ellipsoid has to be bigger than or equal to the accumulation point. Okay, so then in the last few minutes, I wanted to state a result that's unrelated to is not an application of the subleading asymptotics, but because I just defined all of those things about the ellipsoid embedding function and infinite staircases for you, I wanted to say this result that's also in our paper. So if X is a convex toric domain with smooth boundary, then we show that X has an infinite staircase if and only if X is a scaling of a ball in ellipsoid E1, 2 or in ellipsoid E1, 3/2. So if you recall a few slides ago, I stated a result that of Dan that said that a rash yes, a rational ellipsoid has an infinite staircase if it's one of these three things, a ball, an ellipsoid E12, or an ellipsoid E13 halves. But in fact, these are the only convex toric domains with smooth boundaries that can have an infinite staircase. So these guys here are all examples of convex toric domains with smooth boundary. So if it's off the axes, we need the boundary to be smooth. And if it's on the axes, we just need the curve away from the axes to be smooth. Something that we showed is that for an irrational ellipsoid, so if this is E1Z, where Z is irrational, you can never have a infinite staircase. And I'm not going to talk about the much about the proof of this this theorem because it uses different tools than the subleading asymptotics. But I will say like the most simple case is if the perimeter of your convex toric domain equals 0, then that quadratic equation that I showed you, the accumulation point quadratic equation, it has no real solutions. So just from that, then you can, so by the accumulation point theorem, then you can automatically say that your x omega has no infinite staircase. Okay, so yeah, I'm not going to, so the proofs about the fulfilling results that we have in the paper, they consider the obstructions from ECH capacities. Again, if we have a fulfilling, then we know that these leading asymptotics are the same, and so then we can use our subleading asymptotics result to get a obstruction. And the proofs about the infinite staircases, like the proof of the accumulation point theorem and the proof of the theorem I just put on the slides, these instead use obstructions from exceptional classes. And so the proof techniques are a bit different based on what embedding results we're considering. Okay, so some general questions to end with are we study obstructions, as I was just saying, coming from these ECH capacities or exceptional classes, and these both have advantages for various proofs. But some question is, can we better understand the relationship between these two different techniques? So in all of these questions, the obstructions coming from ECH capacities or exceptional classes are sharp in the sense that the best obstruction from either of these two methods is going to like determine if there can be an embedding or not be an embedding. But often, sometimes the ECH capacities method is easier, and sometimes the exceptional class method is easier. And there's not really like a nice way to understand how these obstructions relate to each other. So can we better understand the relationship between these two different techniques? Another question is that we were really hoping to prove, but we were unable to prove, is that if is there a omega with an infinite weight expansion, so that has infinitely many of those BI terms that has an infinite staircase? Another question is, here we are specifically thinking about convex toric domains. So we saw that the subleading asymptotics of the convex toric domains recovered the perimeter. So do the subleading asymptotics of a concave toric domain recover any meaningful information? Another question is, does the lim sup of the EK terms recover meaningful information? So we don't have like that the lim sup is equal to negative some other nice quantity like the perimeter that we have for the lim inf. And then the last question is more about this packing stability. So we showed that these zero perimeter domains can't pack a ball, but when we're trying to pack with these convex toric domains, what can we say more generally? So if our convex toric domain is not a ball, like when do we expect it to be able to pack something else? And so just these more questions about packing stability. And that is all. Thanks everybody for listening.
Thank you. Are there any questions? So maybe I can ask the EKs, if I understand correctly, should be somewhat continuous because the capacity and the volume are continuous, right?
Uh-huh.
But the parameter seems to not be continuous, right? Because it matters whether it's like rational or not, or smooth or not, stuff like that, right?
Yes, that's correct. The perimeter is not continuous. Um, hmm, that's a good question. Uh,
So I guess like the Lee-Minf behave somehow.
yeah, exactly. Uh, but yeah, I guess I have. Yeah, I mean that must be about the limb imp somehow behaving in this way, but I have nothing. Hmm. But yeah, I have nothing intelligible to say about that right now. But but that is a an interesting point. Yes.